So again, this is an introduction to virtual prototyping, modeling, and simulation with MapleSim. So why would we want to do physics-based modeling? So physics helps us to understand how the world around us works. One of the first set of equations that we kind of study in physics is the equations of motion of a projectile. So we have our speed, our position, and our acceleration, and we can use these to kind of figure out the position of things as in time. So for example, if we're throwing a basketball, we can figure out exactly where it's going to be for any given time and how far it's going to go and how high it's going to go. We usually do these with hand calculations, so we'll solve for the velocity, the distance, and the duration. And as I mentioned, we can predict basically the behavior of the system at any instance in time. So why would we want to use physics-based modeling tools if we can do these hand calculations? Well, what if we need to calculate the whole path? So instead of just these single locations, we want to know this line here and where the ball will be as a function of time and not just at certain times. Well, this would be extremely time-consuming. Computers can solve these equations iteratively for us, so why not? And modern technology has allowed the process of building physics-based models to be much easier. So in this case here, I'm just going to show a video of a 4-bar linkage mechanism. So this is a robot that has 4 bars, and it's able to apply a torque, and then it can basically rotate around. And this robot is designed for specific application. In this case here, it's for a contest where we're trying to take these bars out of a slider. So we're just going to loop through this video again, and we're going to highlight the 4 bars in the system. So we have this first bar here, this is the second bar, the third, and then the fourth. And this kind of simple system we can easily model using MapleSim. So we're just going to go through this very quick example. I have here the components that I'm going to be using from my library. So first I'm going to put in some fixed frames. These are going to tell the system that we're attaching it to the ground and that there's not anything attached to the fixed frame won't be able to move. I then want to pull in some link. So we're going to have 3 links that we pull in. These are going to represent the 3 bars that are moving, and then we're going to have the 4th link will essentially be what it will be between the 2 fixed frames. To allow motion between the various links, we're going to add these revolute components. A revolute component, as you can see here, it allows for rotation about a certain axis. So we're going to add 4 of these to connect all of the different links and to the grounds. We're then going to add a path trace. We're going to add 2 of them. What a path trace allows us to do is to visualize the motion by tracing a path in our results. So we add one to this corner here and then over here. And then to drive the system, to give it some kind of motion, we're going to add this constant torque component, and we're going to attach it to this revolute. What this is going to do is it's going to apply a constant torque to this revolute, and it's going to drive the system to produce some motion. And hopefully we'll get some motion that's similar to the video that we saw previously. So these are the results that you get using MapleSim. So on the left, we can see some plots with the angular acceleration and then the angular speed. And we see that if we were to try and calculate this by hand, this would be very tedious and very time consuming. And so this clearly highlights the benefit of using a physics-based modeling tool. And on the right, we can see the 4-link mechanism in action. So on the right here, this is the revolute that we're giving the torque, the constant torque to. And then on the left here is the other trace that's tracing out the path. So you might be thinking, well, that was a very specific example for this robot that's simply trying to take some bars off. But there are a lot of real-life applications for this 4-bar mechanism. Take, for example, a bike. This blue frame would essentially be our fixed frame. And then we would have these 3 bars here that would have some motion and would move around as we're going over bumps. Other examples include the hood of a car. So we have this 4-link mechanism here. And in this case, we're also adding some kind of damping so that the hood doesn't just completely swing open or swing shut. And then on the right, we also have this vice grip. So we have this would be 1 link, 2, 3, and then the 4th link. So we see that this 4-link mechanism actually has a lot of applications in the real world. So again, why physics-based modeling? It gives us a better understanding of physics and what design parameters will affect what behavior. So this allows us to build a model, tweak some of the parameters, and really investigate how it's going to affect the output of the system. It's also going to help us figure out testing kind of what if scenario. So what if we were to increase this mass to an extreme value, or what if we were to apply a force that's very, very high? Would things break? What kind of response will we get? And this allows us to iteratively modify our design. It also allows us to visualize and evaluate design options and communicate our ideas more clearly. So let's say you're trying to build a prototype and you want to explain it to potential investors or to a coworker. Having a physics-based modeling tool where you can visualize it can really help get the point across. And all of this is before the first prototype is even built, so there's no money spent trying to create these prototypes, breaking them, and then having to rebuild a prototype. Everything is done digitally. So what are some common mechanisms that are modeled in MapleSim? Well, on the left here we can see a pulley system. We have a slider crank mechanism, which could be used for a very specific application. And in this case here we can see a CAD visualization that was imported into the model. We can model gear sets. In this case here we have a planetary gear set, hydraulics and pneumatics. So we're using some kind of hydraulics and pneumatics to drive a system. So this could be a simple case of this grabber, or it could be more complex things such as in an excavator. And then also rack and pinions. So these are just some of the examples that can be the different types of areas that can be modeled using MapleSim. So we're going to look at a model here. So we have a trebuchet model. So the trebuchet is a system that has a countermass, has some arm, and then we have a ball that's attached to a kind of a net. And what happens is when we let go, everything swings forward and we can shoot a ball. And we can see here we can see a little bit what we would get if we shot this ball. So what I'm going to do now is I'm actually going to leave the presentation. I'm just going to load up this same results for the trebuchet. So what I have here is a Maple worksheet that's linked to a MapleSim model for the trebuchet. So we see here we have our different parameters that we want to investigate. So the countermass, these two lengths. We have the length of this peg, the mass of our projectile, and then the angle of the peg. What I've created here in this worksheet is sliders that represent the different parameters that we can play with. And once we choose them, we can plot the results. So I'll just plot these same initial results that were shown in the PowerPoint presentation. And then we can add this annotation. So just to know, everything that you're seeing here was completely built using these tools that you can pull from the palettes toolbar. On the left we can see we can add things like plots, buttons, text areas, and sliders. And that's how this entire section was created. So this gives the user a lot of flexibility in what they want to put into their worksheet and how they want to use it for their analysis. So what we can do here is, now that we've plotted this first one, we see that the ball will go to, or the projectile will go to a maximum height of 6.29 meters, and we'll go to a maximum distance of 17.5. So let's say we wanted to change some of the parameters. So we can take a look at our schematic here. We'll make that first arm, we'll make it a little bit shorter. We'll make this projectile mass, let's make it the maximum, why not? What else can we do? Let's increase the counterweight mass as well. So now that we've made all these changes using our sliders, we can actually add the results for the plot. So we see now by making those changes, we actually have a maximum height that's a little bit lower, 5.99, and our maximum distance that it travels is a bit shorter. It's only 15.3 meters now. And so we can continue playing around with these things. You know, right now we're just sliding these sliders around, giving it whatever values, and we can add another plot. So you could really use this to investigate one parameter at a time if you so wished. You know, for example, if we started with this initial setup, we could say, okay, let's add the plot. And then if we want to really just see what's the effect of changing only the countermass. So we'll lower it, plot the results, and let's see what happens. So we see that the ball had a higher initial height, but then doesn't go as far. And we can decrease this further. And this is almost like doing a quick parametric study. So you're changing one parameter and you're checking to see how it affects the system. So based on this, we could say that as we lower the counterweight for this system, we're going to get a shorter distance traveled by the ball. So this is just one of the examples that we can do with the trebuchet model, so I'll just close this for now. And I'm going to go on into building just a very simple system. So this is the canvas that you see when you first open up MapleSim and you just have a new model. So I'm going to go into the library section. So we see here the different libraries that MapleSim has to offer. We have electrical, 1D mechanical, multi-body hydraulics, and many more. In this case, I'm going to be building a pendulum. So I'm going to go into the multi-body, bodies and frames. I'll first add a fixed frame, so I'm going to tell my system that I'm fixing this to the ground and it's not allowed to move. I then want to allow for some kind of motion, so similar to when we did the 4-link mechanism, we're just going to add this revolute joint, and this is going to allow for rotation about the z-axis, so it's just going to allow for some rotation. This rigid body frame is going to be used to represent the thin rod that's going to connect my mass, and this is going to create my pendulum. When you're in the MapleSim canvas, you can arrange your components so that it looks better visually. So in this case, I'm going to rotate my mass so that things can kind of line up a little bit better. And then one thing we can do is we want to get some information from the system. So we can add probes. So in this case, I'm going to click this little probe icon here. And when I get near these kind of connection points, they highlight. And this tells me I can attach a probe. So in this case here, I want to measure the angular speed, and I'll attach a second probe on the mass, and I want to measure so this length here, this is going to tell me the position in the X and the Y axes. So I'm going to run this simulation, so I just hit this play button at the top, and we can see that MapleSim is doing its calculations, and so we see we can get these, make this full screen. So we get these results for the system. So probe 1, this W, this is my angular speed. So we see it just kind of it fluctuates up and down. And then I have my position X and my position Y. One of the neat features about MapleSim is we have this built-in, let me just get this visualization. We have this built-in 3D playback window, which you can access from the plot windows on the left. This allows us to visualize what we've created. So in this case, we have this, where is my, sorry. Sometimes the play buttons like to disappear on you. So here we have our pendulum, and I'm just going to hit the play, and it's going to animate the simulation. So I'm just going to toggle these off to make this look better. There we go. So we see we have our pendulum swinging back and forth. There's no damping in the system, so as you expect, it simply swings back and forth, and we'll continue doing this forever. So let's say we want to make this a bit more complicated. Instead of a single pendulum, let's make it a double pendulum. So we'll select all of our components. I'll use Control-C to copy and then Control-V to paste. And I'm just going to connect the two of them as such. So now what I've created is, this is my first pendulum and this is my second pendulum, and they're connected in series. So now when I run the system, we're going to see a visualization for a double pendulum system, which is much more complicated than just trying to solve a single pendulum. So now we see the motion is much more difficult to describe, and this gives you a lot of intuition as to what's going on with the double pendulum system. And what I will actually do for this is I'm going to change it to 12 seconds, because if I remember right, if you change it to 12 seconds, you can see the bar do a complete flip, and everyone likes to see that. So we'll try this. So hopefully I was correct. And it's kind of going to be near the end of the simulation where the second bar is going to do a complete revolution. There we go. Yeah, so there you go. So that's one of the fun things you can kind of explore with MapleSim. You can have these visualizations, you can kind of see what's happening, and you can maybe see some interesting things like this. So now I'm going to move on to my next model, which is just a very simple model for house heat transfer. So on the left here is just a very simple description of what we're trying to model. So we have some kind of house. We have two walls that we allow heat to transfer through. Each wall has some resistance, R1 and R2, so that's basically your insulation. And this Q1 and Q2, that's going to be the heat flow in and out of the system, out of the house. So what I've done on the left is I've used this heat capacitor. That's going to represent my house and its ability to retain heat. I've added these two thermal conductors. This is going to allow for heat flow between the outside and the house. And then I have this ambient temperature, which is just a fixed temperature. All of these components were pulled from the thermal library. So on the left, if you drop down thermal, heat transfer components, we can see the heat capacitor as well as a thermal conductor. And in the sources, we can see our fixed temperature. So these are the components that I used to build the model. So I'm just going to run the simulation now. And we're going to see how the temperature inside the house changes. So we see that we have this decreasing behavior. And down here, the red line, this is our ambient temperature. And the green line is our house temperature. So what we see is the house is initially starting at a warmer temperature than it is outside. These measurements are in Kelvin, so it's not 305 degrees outside Celsius, it's 305 Kelvin, which is in the 20s Celsius. We see the temperature decreases initially quite rapidly and then slowly approaches the outside temperature. Things like the initial temperature of the house, we described it here in the parameters, so using tHouse. And the things like the resistance are R2 and R1. So these are all parameters, and we've defined these in the model. So this allows us to quickly change the parameters of the system. So let's say we want to change the temperature of the house from 305 Kelvin to, say, 350 Kelvin. We could easily do it by just accessing these parameters and then rerunning the simulation. And in this case, what we expect is that the initial temperature is higher, but that we still have the similar behavior. And that's exactly what we see. So one of the main advantages of using MapleSim is that the calculations are done using our Maple engine. And our Maple engine is very strong, especially in particular symbolically. And so we want to take advantage of that in this case. What we'd like to do is know what are the equations that are governing the behavior of this system. So what I'm going to do is I'm going to go here. So on the left-hand side here, we have this last tab, which is for apps and templates. And we have one built in that's called equation extraction. So I'm going to double click to open this. Okay, so it's just loading. Double click it again. All right. So we're just going to let it kind of load up. So when we see that it's ready here, we're going to load our system. So this is telling the app that we want to connect to MapleSim and we want to pull in the system that we had modeled. So what we have here is we have our variables, which is our house temperature, and we have our parameters C, R1, R2, the ambient temperature, and then the house temperature. So when we scroll down, we can just simply click Extract Equations. And we see here that the app has given us the equation that governs the temperature in the house. It's a differential equation, so we have one derivative in time. And we see that it's taken the values that we've given our parameters and it's populated it into our model. Well, let's say we wanted to know how certain changes in parameters are going to affect the behavior of the system, and we want to really just see those symbolic variables. If we go back up to the parameters section, we can simply click Toggle Symbolic, and that will just make all of these retain their symbolic nature and not substitute in the value of the parameter. And if we re-hit Extract Equations, we see that we get an expression that shows us exactly what the differential equation is for the temperature in the house. So we have our R1 and R2, the resistance of the walls, C, which is the capacitance of our house, so the amount of heat that it can hold, the ambient temperature, and then the house temperature. So I'm just going to close this app now, and I'm going to modify the system a little bit. So I'm going to show how easy it is to really change the system that we're analyzing. So I'm going to go into the thermal library, and I want to add some sources. So I'm going to add fixed heat flow. So we can add these simply by clicking and dragging and placing. And if ever you're looking for a component but you're not sure where it is, you can simply go at the top here and search. So we can go fixed heat. You can use keywords and it'll populate. So here we see, it gives us a little picture. Yes, this is exactly what we want. Click and drag. And now we've added 2 fixed heat flows. So I'm going to connect both of them here. And I'm going to give them 2 different values. So I'll give this one 10. So this is going to have a positive heat flow, and then we'll add a negative heat flow. So what I'll do is I will save these results. I'll just call them original. And then I'm going to rerun this simulation. And we're going to see how adding these fixed heat flows is going to affect the response of the system. So we see our original results, we had a decrease in the temperature and eventually it went towards the ambient temperature. But now that we've added an overall positive heat flow into the house, we see that the temperature is actually increasing and then slowly goes towards an equilibrium. So we will then, one of the things we can do is we can say, okay, well, let's say we don't want one of these heat flows. So we will take out the positive heat flow. So we don't want to add any heat into the house. We can simply disable it by clicking on this little symbol here. And when it becomes translucent and no longer solid, this means that the component is turned off. So at a simple click of a button, we can turn things on and off in our model and see how it affects the behavior. So now that we only have a negative heat flow, we expect this will be pulling heat out from the house. And so we don't expect that the heat is going to be increasing anymore. And so as we suspected, now that we have taken out that positive heat flow, we see that it's decreasing. So this just shows you the simplicity in which you can kind of modify the model and you can really just add things and remove things very quickly and how it's going to affect the response of the system. So I'm going to move on to my next model now, which is heat conduction along a bar. So what we've done here is we want to look at a bar that has some initial temperature, and then we're going to heat it up from the left end using a fixed temperature once again. And we want to measure the temperature at the right end of the bar. And the way that we've modeled this bar is we've discretized it, so we've cut it up into various sections, in this case 10. And in each section, so if you double click on these subsystems, this allows you to investigate what's inside of them. What we have is for each little section of the bar, we have a heat capacitor, so it's going to be able to hold some heat. And then we put some thermal conductors so that it can transfer heat to the left and to the right. We then also add this temperature sensor, which allows us to make a measurement of the temperature at this location. So we will run the simulation now. And what we expect is, so this bar was initially cooled, and then we're adding some heat to the left. So we expect that the bar is going to slowly heat up, and indeed this is what you see. So this is the temperature at the end. We see it starts with some initial value, and we can zoom in. So it starts at 273 Kelvin. It slowly increases and then reaches the steady state. And the steady state in this case, we can check the value by using this drop down here, choosing the last option, and this is going to allow us to see the value. So it's 372.999, so 373. And we expect this because our fixed temperature is parameterized by T boundary. And if we check this parameter block, our T boundary is 373. So it makes sense that the end temperature wouldn't exceed the fixed heat that we are applying to the left end. So we have a couple of attached files here that I want to investigate. The first one is some animations that I've created using Maple worksheets. So I will click Simulate. And again, this is going to connect the Maple worksheet with my MapleSim model. Once that's ready, the Animate button turns on. And when I click it, what we're going to see is this is a color visualization of temperature. So blue is cold, red will be hot. The middle plot is going to show the temperature at the 10 discretized locations as a function of time. And the final plot is going to show us the temperature for each of the positions as a function of time. So I'll hit animate, and it's going to run for 2 seconds. So we see on the left that the bar is slowly heating up. The left end becomes red much quicker because that's where the heat is being applied, and the right end takes a bit more time. In the middle plot, we see that all 10 positions initially slowly ramp up, but then all become close to the equilibrium of 373. And then on this right-hand plot, we see that the temperature across the bar is slowly going up to reach that equilibrium temperature. So we'll let the simulation finish out, and then what we can do is play. I've created it so that you can take this slider and you can slowly move it around to see where the system was at that particular time. So let's say we want to know exactly what was happening at, let's say, half a second. We can see that after half a second, this is the distribution of the temperature in the bar. So we see it's 373 at the left end because we're applying the heat there, and it's slowly tapering off, but it's slowly increasing with time. Here we see with all 10, with the 10 measurement probes they're giving us, and we have our 3D visualization. So this is just one of the neat things you can do with MapleSim and Maple worksheets is you can add these sliders and you can add whatever custom components you want to really help you analyze the system in any way that will be beneficial to you. So we won't save any changes here. Now open the second one, which this is showing the accuracy of our MapleSim model with respect to an analytical solution. So using math and solving it by hand, what would we get? So on the left-hand side, we define the thermal diffusivity. So here we'll just keep it as 1. And using Maple, so these are all Maple commands, we can define our 1D heat equation. So here we have partial derivatives, and U is the temperature, X is the position along the bar, and T is time. And this is a very well-known partial differential equation, and we can define it in Maple. We want to apply some initial boundary conditions. So in this case, initially for all the system, we have it at 273 Kelvin. At the left end of the bar, we have a fixed temperature of 373, so that's our fixed temperature. And then this D1 is our derivative, and we're saying that the derivative at the right end of the bars is 0. Then what we could do is we can tell Maple to solve this numerically. So we use the command pdsolve, and we give it the PDE, the initial boundary conditions, and we tell it basically our time step and how far we want to go in time. Then once this is done, we can plot the results, and these are the results that we get analytically. On the right, we have the simulation using the MapleSim model. So these are some commands that you can use to, the first one links your model, so that tells the worksheet that we want to connect, to our MapleSim model. And the second one just tells us that we want to simulate it. When we simulate, what we get is we're plotting the end temperature, and we see that these two results match very closely. So we can actually highlight the plot, copy using Control-C, and then paste using Control-V. And you can see that the results match almost perfectly, if not perfectly. So this really shows that the strength of using MapleSim and how accurate it is when you're building up these models. So close this worksheet. So now we'll move on to a more complex example. This example you can find in the help, and then under examples, physical domains, multibody, and it's the last one at the bottom of the list. So this 5 degree of freedom robot. So this is where this example comes from, and we see it's got a lot more components to it. So I'll just move things around here. So what this is we've created a robot, and we're going to give it some kind of motion that we want it to track. So on the left here, we're giving it some signals. So a sine wave, this is a ramp. All of these are actually ramps, and so this is just telling it how we're going to control the motion. These subsystems here have PID controllers in them, and so it's going to take in our desired position, and it's going to calculate what type of what we need to apply to the motor so that we can get it to the desired location. And so all 5 of these are essentially a shared subsystem, which means they're all exactly the same, and if you make changes to one, it'll change all of them. So this is very beneficial if you have a system like this where you want to have the same type of controller for all the different components, but if we make a change in one, we don't want to have to go through and click on each one and change each one individually. This will automatically do it for us. So we have all these different parts. On the left here under attached files, we can see all these STL files. This is because we've imported some CAD, and so this gives us the STL files and will give us a visualization. So I'm going to run the simulation, and what we're going to see is a robot that tracks a certain motion profile. So I'll just hide these for now, and I'll give you. So when I hit play, we see that the robot is going through its motions, and we can change what kind of motion we would want to give to this by simply changing those ramp parameters or the sine wave parameters. So this, the first initial motion, that's all due to the ramps, and then this sine wave is what's going to give us the little wave from the end here. And then another thing you can do within the analysis window is we can create plots to not just of our probes, but also generate plots that will be useful for us. So let me just... So what we have here is we've created different plots for a plot for each of the various positions. So these are different angles that we want to match. The red for each of them is the desired, so those ramp functions, and then also our offset sine wave. And the green is the actual response of our system. So using this, we can see how well the system matches for each of the different locations. So we see here there's initially a bit of an undershoot, or it's a bit under the expected value, and then it goes over. So this tells us that we can maybe tweak the parameters in this given controller so that we can get a much more a response that's much closer to what is actually expected. But we see that overall the system is doing a very good job. And so this just really shows the power of MapleSim and the complexity that we can really bring in and use in the MapleSim environment. So I'm just going to go to some final examples now. So we're going to pull up this, it's the Now robot. So this is a humanoid robot that's been developed, and we're able to make it do a lot of different things. So I'll just kind of explore the robot a little bit. So we see we've made the head from these various components. We've added some CAD geometry. So you, in addition to having them attached simply, on the left you can usually see which STL files you have, and they're usually imported into the system by these CAD components. And so each of these various parts are just modeled individually. The Now robot is one of the models that you can find on our model gallery, and you can download and interact with and play with. So in this case here, I am looking at the model where the robot does some Tai Chi and walks. So let's start with some Tai Chi. So I've already ran the simulation previously and I've saved the results, so I can just toggle visibility will allow me to see the results of the simulation. So in this case, we're going to see the Now robot do some Tai Chi. The arrows that you're seeing at the feet, those are basically force centers, so it's measuring how much force is being applied at each of these locations. And then we can also see the robot walking. So as I mentioned earlier, now that we've toggled the visibility of two different simulation results, we're going to see them overlaid on top of each other. So we'll restart the animation, and now we'll have two robots. One's going to start walking, and the other one is going to do Tai Chi once again. Being able to save multiple simulations and then overlay them like this is very beneficial when you maybe make some small changes to a system and you really just want to see how the changes affected the results. So close this, and then we have a bit of a more complex one where we have the Now robot playing volleyball. So the ball is sent towards the robot, and the robot swings and returns it. So we can see here that we have the ball, it's in the air. So once you're in this 3D playback window, you can use commands such as Shift-click to move side to side, Control-click to rotate, and this allows you to easily move around in the 3D window. So we have this ball up here, we've designed the court, and when we hit play, we see that the robot swings at the ball. So we'll watch that one more time. I'll slow it down so you can see it a bit better. So these are some of the neat features that we can, if you put in the effort, you can really get a lot out of MapleSim. You can do very simple models like we showed earlier with the single and double pendulum. You can have much more complex things such as this Now robot, or you can have the 5 Degree of Freedom robot where you have some nice CAD visualization. So I'm just going to return to my PowerPoint presentation now, and I will, from this current slide. So what are different industries that are using MapleSim and our product? So we have vehicle companies, so for powertrain modeling, humanoid robots, so similar to just like the Now robot that was shown, you can do a lot of these complexities. We do off-road applications, so MapleSim has a tire library that you can use for modeling tire contact in vehicles. We have batteries, we have a built-in library for batteries, which can be used to model like lithium-ion batteries, very common batteries, and lots of the chemical behavior and the thermal behavior is going to be built into these. Another interesting aspect is, let's say, for example, you wanted to put a certain battery, but the type of battery that you want to model isn't quite there. You can use a custom component and really just define the chemistry and anything that's going on that isn't quite captured by our built-in library, and make it really unique and really your own, and really customize it towards your needs. We can use it for construction applications. So for example, if we want to model an excavator, we can see how much load can we put into the bucket before things start to break, or before the mass is too large and it starts tipping things over. And then also vehicle stability, so we can use it for control applications, and build up controllers that way and see what works and what doesn't. So just to wrap things up, physics-based models can be used to visualize, communicate, and evaluate design options. It allows you to better understand your system's behavior, and you can test out designs before building. So that's a lot faster and a lot more cost-effective if you can simply tweak things very quickly in a MapleSim model versus having to build and reiterate. So, and this also extends the capability of other tools. So, for example, we saw that we were able to import some CAD geometry, and so we can design things in CAD, simulate it in MapleSim, analyze it in Maple, and then deploy it to real-life physical systems. So we're really taking different components to really give us the tools we need to develop something that's very, very well thought out, very well engineered, and has been analyzed and won't fail on the first prototype. So what are some of the next steps? So discover the various applications through the online model gallery. So maplesoft.com, you can find the model gallery, which is where I pulled all of the examples that you saw today. You can access the exclusive global MaplePrimes user community for questions and support, and to help others with their challenges. So that's just at mapleprimes.com. And again, just have fun and learn lots.